We're going to learn about Gaussian elimination. We're going to partake in the first video of a series of videos, and this one is an introduction. We're going to look at, along the way, this idea of augmented matrices and EROs, elementary row operations. And we're going to end up in a form called row echelon form. So firstly, Gaussian elimination came from the famous mathematician Carl Gauss, who was one of the greatest, undoubtedly one of the greatest mathematicians. And he started the work on this process. Other mathematicians, such as Jordan, added to what Gauss did. And there's a whole lot of history you can read about that's outside the scope of this video, but that's where it gets its name, Gaussian elimination. Gaussian elimination is often used to solve a certain number of equations across a certain number of unknowns, which we started addressing in the previous video. So you see an example there, a system of equations. This one is three equations across three unknowns, x, y, and z. Usually that's the starting point, 3 by 3s, and it's also where we're going to be focusing most of our time. Usually with two equations and two unknowns, we use the traditional methods of simultaneous equations with elimination and substitution. This is instead of using an algebraic approach. So it's for solving three equations and three unknowns or more, but it tends to be a more efficient and effective method. It can go beyond 3 by 3, of course. So the process involves converting the system of equations into matrix form. So we do a simple conversion. So from your work in matrices you've done before, you know what a 3 by 3 matrix is. So what happens is the coefficients of x are in the first column. You can see there that the coefficients of x, if we go down, are 1 in the first equation, then 2, and then 3. We then go for the coefficient of y in the second column, 1, 4, and 6, and then 2, negative 3, and 5. We list those in there. Now normally in matrix we'd put another edge, another brace on there to close the matrix. These ones are called augmented matrices. Augmented basically means extended. So we put just a vertical partition, a line, and we leave the room for another one column and close the matrix there. And the answers, or the solutions to the equations, or I should say what they're equal to, the D coefficients, are all listed as such, corresponding to each equation. So that's an augmented matrix. What we need to now do is learn about the EROs, or elementary row operations. These are the things that you can do. These are valid procedures that you can use. Oh, and I've just spotted a little error. That's minus 5z there, so that should be a negative 5. Whoops. Make sure you change that if you had the wrong sort of sign on the 5. Okay, so getting on to elementary row operations, you can interchange two rows, because that's like if you are looking at a system of equations using simultaneous. That just means you swap the order of the equations, and you probably appreciate that makes no difference. You can do that. Sometimes that helps in the Gaussian elimination process. You can multiply a row by a non-zero number, so you can multiply all of the terms by that same number, and you've still got the same relationship between x, y, and z. So that's fine to do, and you can add a multiple of one row to another row. So make sure you are well versed in those three EROs. Interchange two rows, multiply a row by a number, and add a multiple of one row to another row. So let's go through the process of our first go at Gaussian elimination to solve the system of equations and see what the solution looks like. And basically what we do is written there. We apply the EROs in a stepwise manner. Don't rush through and do multiple things in one step. Keep the steps separate, discrete. Okay. we're going to form a new augmented matrix such that the entries below the main diagonal, top left to bottom right, are 0. So all the entries below, this being the main diagonal, all those entries below need to be turned into 0, and there's only 3 of them in this one. Okay, in a larger system it's a bit more work than this. So our first step, we form the basically that's step 1, we form the augmented matrix, so we did that already. And secondly, we write in the top row, it stays the same. We need to look at this entry here, and using one of the EROs we need to make sure that becomes 0. We leave row 1 as it is, and we look at row 2, and I'm going to call it, use notation like this, R sub 2, which means row 2, and I'm going to use ERO number 3 there, add a multiple of one row to another. Now when we say add, if you add a negative multiple, it's subtracting. So basically if we write row 2 minus 2 row 1, let's see what happens to row 2. So what that means is that row 2, which is 2, minus 2 row 1. So in row 1 just above the 2 is a 1. So if we multiply that by 2 we get a 2. So that would be 2 take 2, which is 0. So we now have a 0 here, which is what we want, because we want these to become 0 below the leading or main diagonal. Okay, so we've got that there, and we have to do it with all the other corresponding ones. So we have 4 take 2 is 2, and negative 3 take 4 is negative 7, 1 take 18 is negative 17. Okay, so what we've done is leave row 1 and row 3 alone. Just go step by step, especially as you're learning this. Okay, a big mistake, rookie error, is to try and combine several steps when you should have just done one at a time. Okay, that's not going to lead to good things. Okay, for now we've got row 1 and row 2 right where we want them. We're going to look at now at row 3, and we need to get that 3 there into the form, which means that we need to find a 0. Notice how I'm going straight down. I don't go across to the 6, I go straight down. After we go straight down, later on we'll go across that way. Remember that for now. More about that later on in another video. Well, one way to get that 0 is to go minus 3 times row 1 using the same type of ERO. So that would be 3 take 3 is 0, that's what we wanted. 6 take 3 is 3, and negative 5 take 6 is negative 11. We have 0 take 9 by 3 is 27, that's negative 27. Okay, we're getting ready for step 4. We've got the 2 zeros there where we want them. We need to get a 0 here. So what I'm going to do is multiply row 2 by 3 and row 3 by 2. So let's execute that. So that keeps the zeros the same, which is good, because if you started adding things to that, that may not hold the 0. That'll be 6, negative 21, negative 51, and row 3 by 2, 0, 6, negative 22, negative 54. Now using ERO number 3 again, adding a multiple of one row to another. That multiple can be negative 1, by the way. That means we do the following. We go row 3 minus row 2, because I just only want to affect row 3 because row 2 has the 0 where we wanted it. When we multiplied it by 3 in the previous line, I knew that wasn't going to upset the 0, but it means we can go row 3 minus row 2. So we've got the 0 that we had there before, and it's not affected by the 0 above, and we get that next 0 now. So that required a bit of thinking, and negative 22 minus negative 21 is negative 22 plus 21, which is -1. And we have -3 over here. Now, when we've got that form, that's the form we wanted, you might remember, we can say that it's in row echelon form. So that's an example of row echelon form. So that means that the row leaders, which are 1, 6, and -1, occur one spot further to the right compared to the row leader from the row above. So this one occurs here in column 1, the next row leader 6 occurs in column 2, and the next row leader -1 occurs in column 3. And to the left of those row leaders are always zeros, or it's the edge of the matrix as per row 1. So that's row echelon form, and then it gets pretty easy to determine the solutions. So that means that -z equals -3. So therefore z is 3. And then we can sub that in to the other rows to get y and also x. So y equals 2 and x equals 1 by substitution, done successively. For example, to get the y equals 2, subbed in 3, so -21. So what you'd be doing would be going the -21 times 3, and we have to go 6 times y plus -21 times 3 equals -51, and so that's -63. There's a gap of 12, so y has to equal 2. So that's where we get those results from. Okay, that's not part of the actual problem directly, but that's how it would work algebraically. Now, because you saw that I had to do that, you might be thinking there's got to be a better way. That wasn't really that helpful. Well, what we do next after that, which is not in this video, next would come what's called reduced row echelon form, and that means we end up with a matrix is in this form here, where we have something that looks like the identity matrix and the solutions there that would give you the actual values of 1x, 1y, and 1z.